This is what we've been talking about for the last few weeks. These, as I'm sure you've come to see, these three equations can describe a whole lot of different stuff and make a whole lot of complex problems. But at the end of the day, really everything we've been doing is based upon these three things. Velocity is a vector that describes some change in position, like some translation, over a change in time. Right? Our delta x vector just tells us where I moved, and so how far and in what direction. And then if we divide that by the amount of time it took, we get our velocity vector. So delta x and velocity are vectors that are in the same direction. Then momentum, building off of velocity, we just multiply it by mass, which is a scalar, right? So we kind of just stretch the velocity vector according to the mass to get our momentum, so another vector that's in the same direction as velocity and delta x. But momentum is helpful because it not only tells us how fast an object's moving, but how much like inertia it carries, like what effect it will have on other things. How hard is it to move this object? How hard is it to get it to stop? So on and so forth. So momentum we found is very useful, especially when it comes to collisions. And then how does momentum change? Well, we apply force or forces, but some net force over a change in time causes a change in momentum, a delta p. So F net and delta p are in the same direction. Whatever direction I apply the force is the direction of change in momentum. But you can have any starting momentum, and of course the final momentum depends on both the initial and your delta p. Are there any questions about anything on this slide? So now we're going to take this and describe, we'll try to use a similar system to describe rotations and angular motion. So what does that mean? Well, think about a ball rolling down a hill, right? So far we have the tools to describe the movement of this ball, like its center of mass, translating down a hill. We have the force of gravity, we have a force of friction, we can describe its speed, we can describe the angle, we know how to break it into components, how much is horizontal, how much is vertical, all that stuff we've covered. But what we don't know really how to talk about is that this ball is spinning, right? That's a whole other aspect of this motion that turns out to be really important. How do we know that's important? Well, we're not really going to talk so much about rotational kinetic energy, but that's maybe one way to think about it. If this ball gets to the bottom of the hill, and then we just pick it up, it can still be spinning. I guess what I mean to say is that spinning does carry energy, right? If I have this chair here, and I do this, something physically interesting is happening. But our description of this would just say its velocity is 0. And that's not really the full story. So we want to develop a set of tools or a way of describing that. And turns out we can treat it separately from linear momentum. So just like we broke problems into a vertical and a horizontal, or x and y, when we talk about a system, we can describe the rotational aspects of it and the linear. And of course, there's going to be ways that they can come together and we can break them apart, just like with x and y components, but we do deal with them separately. So I'm just going to run through what all the things we're going to build up are, and then kind of start back at the beginning. But very quickly, when it comes to velocity, instead of describing a translation from one point to another, we're going to describe a change in angle. So rotation divided by time. So this omega, this curly w, is a vector that describes how fast something is rotating or spinning, right? We'll talk about how to describe the direction and everything later, but at the end of the day, we have a magnitude, how fast, and a direction, because things can rotate in different directions, right? I can spin this chair like this, or I can, if I wanted to, rotate it end over end, right? I can do anything I want. And I need a way to describe those different directions of rotation. So we want it to be a vector. In addition to the velocity, I want to have some concept of angular momentum, right? And some things are harder to spin than others. If I have a carousel and this chair both rotating with the same angular velocity, like the same amount of revolutions per minute, it's going to be a lot harder to stop the carousel than it will be to stop the chair. So there's clearly some difference. And so that's where this I, rotational inertia, or moment of inertia, you also might hear it called, but it's basically our angular mass. and or rotational mass. And when we multiply that by our angular velocity, we get our angular momentum, which is capital L. That's also a vector, but that's our concept of motion, rotational motion that depends on the rotational mass, this I. And then finally, we have things that cause a change in angular momentum, right? Things can start rotating faster or slower, and those come from torques, which is our rotational force. So if I apply a net torque to something over an amount of time, then its angular momentum L will change, and we'll get a delta L. So it seems different variable names, and they mean different things, but very similar structure, where we have change in angle giving us a angular velocity, like that over time gives us an angular velocity, multiply mass, angular momentum, and we change it with some sort of angular force times an amount of time. So let's build the, yep.
So torque is a change in rotational force, like net force?
Torque is like a rotational force. We'll build up to torque. We'll talk about that more soon. But first, let's start way back at the beginning. We know we have angles. Very quickly, we're describing angles as magnitude and direction. So magnitude, we have degrees or radians. We're going to deal with radians in this unit. I mean, you can always convert to degrees, but the reason is because degrees are a unit. It's just some arbitrary, I'm going to say one full rotation is 360 degrees. There's nothing physically special about 360. Someone just picked it. And it sucks, and so we're going to not use it. We're going to use radians, which also is not particularly pretty to look at, but the special thing about radians is that it relates the diameter of a circle to the circumference of a circle. In other words, it gives us some relationship between linear change and angle. Like pi is an actual physically important unit, if you want to think about it. And so radians are actually dimensionless, and we can just use them in equations without having to do any conversion. We'll see clearly what that exactly means soon, but we're going to use radians. 2 pi is equal to 360 degrees, or all the way around. So pi over 2 is 90 degrees. Pi is 180. Yeah. Yeah. No, they're not a unit. Yeah, it's more of a ratio than anything. I don't know. You can go down a rabbit hole learning about like pi and e and all these like special numbers, but for our purposes, it's just very helpful for relating angles to distances. Okay. So we know how to describe angles. We've been doing that a long time, and we're going to continue to do it. But we do need a new way to talk about the direction, right? Now things are spinning, and we need a vector. But how should I decide what vector quantity, what direction the vector of this spin should point? So things we want it to do are to be the same for everyone, right? Whatever definition, whatever convention we come up with for describing the direction of a rotation, one thing is that it should be the same no matter who's looking at it, right? I don't want, just because I'm standing on this side and you're on that side, or if someone was below or above, we should all agree on the direction of this vector, right? Just if I'm walking this way and you draw a vector to denote my velocity this way, we would all agree on what way that vector points. And so that's important. What's one way we normally talk about the direction of spin? Well, clockwise and counterclockwise, right? That's a very typical way to denote which direction we're rotating. So if we look at that clock, we ask, well, it's kind of built in the definition, but if we ask what direction are these hands spinning over time, and we would all say clockwise, right? And we'd agree. But that definition is no good for us because it actually does depend on where you're sitting. We are all on this side of the clock, and so we agree. But let's say I'm the clock. Like, let's say my hand is the second hand, whatever. I'm now in the back of it, and you're in the front, right? So for you, this is clockwise, right? My hand is moving in the direction that you would call clockwise. But for me, this is counterclockwise, right? If you look at it from my perspective, I haven't changed. This is now counterclockwise. So what I'm trying to point out is that clockwise and counterclockwise change depending on where you're looking at them from. And so that's not a good way to describe this. What about left, right, up, down? What do I mean by that? Well, this chair is rotating. Well, this arm right now is rotating that way for me. So like, what if I call this forward rotation? Well, now it's rotating left, now it's back, now it's to the right. So that's like constantly changing. So what I mean to say with this is we can't just pick an like a piece of the object that's moving and like attach the direction of rotation to that, because it's always changing and it's just not consistent. How do we know like what part of an object to pick? I don't know, it's no good. So we need something new, something else to describe the direction of rotation that's the same for all observers, and it turns out that the right hand rule gives us a way to do that. So the way we apply it is you just take your right hand. We're all going to use our left accidentally at some point, but try not to. Maybe for the next couple weeks, just handcuff it behind your back or something. You don't need it. And use your right hand and you wrap your fingers in the direction of rotation. So for this chair, rotating like this, we want to wrap our fingers as if they were rotating like with it. And so we get, and then our thumb points in the direction of the angular velocity and the angular momentum. Right, so this will be up. So you should all test that and see if you can find that for yourself. If this chair is rotating this way, we should all get up. And that's true whether you're sitting there, or over here, or under here. It doesn't matter. We all get up. And now what if I reverse the direction? So this is up. If I reverse it, now I wrap my fingers in the direction of rotation, and I get down. And we all should agree on that. If you're using your right hand, we should get down. And so we find that the direction of angular momentum, angular velocity, a good way to describe that is with this right hand rule, and we get an answer that is perpendicular to the plane of rotation. So let's try with this clock. Then what direction is the angular velocity of the hands? So I wrap my fingers, and it can get awkward sometimes. If you ever find yourself like can't quite get it to the right way, there's an easier way to do it. But if your fingers wrap in the direction, we should get that the angular velocity vector of these hands points into the wall. Right? The plane of the rotation is in the plane of the wall, and our angular velocity vector points into the wall.
So it's the bottom that follows the rotation.
Yeah, or all your fingers. Yeah. So fingers curl with the rotation, thumb points in that direction. Like I said, it obeys we all get the same answer, and it also obeys some simple logical things that we want. Like I proved before, if we reverse the direction of rotation, we flip the sign. We go up to down, or in to out, something like that. So that's good. And you could do a lot more thinking about this, but I just kind of want, like, by doing this little demonstration of proving that it's the same for all of us, I just wanted to show that this is, having it be perpendicular to the direction of motion is kind of, maybe not intuitive, but natural. It's required for us to really describe this well. We're not going to talk so much like positive and negative. We could, but that really requires us to like call, like if we're thinking about the page, like most of our problems will be drawn in the plane of the page, rotating this way or that way. And so we'll get directions of angular momentum and velocity into and out of the page. So we could call that the z-axis, really, if we wanted to. We've probably seen that, like x, y, and then z is in and out, but it gets a little bit unwieldy, and this class doesn't require that much math out of us. Well, I guess that's relative to everybody, but we're just going to call it into and out of the page and know that those are opposite each other. These two symbols we'll use a lot. Into the page is a cross and a circle, out of the page is a dot. It's been described to me like if an arrow is traveling toward you, like out of the page, you'll see the point. If it's traveling away from you, into the page, you'll see like the feathers or something for any of us who have been shot with arrows or shot arrows at people. I guess that's how old this analogy is. That's what people were used to back then. But it's helpful. And like I said, it kind of takes us out of having to think about a third dimension and just gives us kind of this binary in or out that's easy to work with.
So can we still use like positive?
Well, let's wait till we get to problems with it, but generally we don't need to call one positive or negative. Like when we end up like balancing things, we'll just usually like set into the page equal to out of the page in order to say that there's no net or something. We'll talk about that later on. Yeah, I mean it is that. All right, so let's just do a practice. If this car is moving forward, what direction is the angular velocity of the wheels? So this should be a quick one. This car is moving to the right. What direction is the angular velocity of the wheels using the right-hand rule? Wrap your fingers with the direction that the wheels are spinning. Yeah. Exactly. All right, so I'll stop us there. You did a good job with this. So if this car is moving to the right, we wrap our fingers in the direction that we know the wheels are going to spin, then we get into the page. And that, I mean, we should see right now, I'm facing you the opposite way, and I agree. If I was here, I also get into the page. So you can see if you're like trying to, I could also do it like this or like this. If you're ever in pain, then reset and try again. Okay, questions on the right-hand rule. So again, it's the biggest mistake with this is not applying it wrong or right, it's just using the wrong hand. That's where we often get into trouble, especially because most people are righties. So you have to stop for a sec. Okay, so now we have a way to describe angles, both magnitude and direction. Magnitude, it's simple, just how many radians, like how big is the angle, and divide by time to get angular velocity. And yeah, I mean, that's it. Angular velocity is this curly W, like I said, omega, and it's in the same direction as the change in angle. So in this case, we just have like kind of a hoop that's rotating around the center here. If we wanted to find the angular velocity, we would just take this delta theta here and divide it by the amount of time. We know if we curl our fingers with the direction of this rotation, we get some angular velocity out of the page, which is how we would denote that. So the units are just inverse seconds, or 1/2 because radians are unitless. This delta theta has no units. And we'll see that's very important when we're relating like linear and angular values together. But if you want to think of it as radians per second, that's somewhat helpful and easier to like say and make sense. But the units really are just per second, angle per second, the angle not having a unit. All right, so that's our angular velocity, pretty straightforward. Let me give you a practice question that kind of requires a calculator. Definitely requires a calculator. If you don't have one, you can just set up the problem and not carry it out. But what is the angular velocity of, and I should say hour hand, of this analog clock in inverse seconds? So it takes 12 hours for the hour hand to complete one full rotation. What is the angular velocity of that hour hand in radians per second, or inverse seconds? So we know the angular velocity is the change in angle divided by the change in time. give you 30 or so more seconds. And the important part is the setup. All right, I'm going to stop us there. First, let's all agree on the direction. So the angular velocity here, if we use the right-hand rule, should be into the page. Right? Can we all see why that is? So wrap our fingers in the direction that the hour hand is going to move, and we get into the page. So now we just need to do the problem. We know angular velocity, we get our change in angle over change in time. So we could pick kind of whatever we want here, but maybe the easiest one, how long does it take to do a complete rotation, right? So to go once around the whole clock, that would be 2 pi. The change in angle is 2 pi going 360 degrees. And then the delta t then is 12 hours. Right? We know the hour hand takes 12 hours to go around. So I just need to do some unit conversion here. 12 hours times 60 minutes per hour times 60 seconds per minute. So that'll give us the amount of seconds it takes to go around once. And so this is the important part that I would have wanted you to see. But we get then a final answer that is A. So 0.000145 inverse seconds, or radians per second. So really a very small angular velocity, which we might expect because you could stare at the clock all day and you won't ever notice that hour hand moving. It's got a very, very small angular velocity. I asked for it in inverse seconds just to give you some practice with identifying these, but I mean, the most simple answer of just what's the angular velocity of the hour hand could just be like 2 pi over 12 hours, right? That still is like an angle over a change in time. But because we wanted the units of inverse seconds or radians per second, we had to do this unit conversion. I could have also picked pi here. So how long does it take to go halfway around? In which case I'd put 6 hours here, and I'd get the same answer. Or 4 pi, 24 hours. I could have picked 1 hour, and then I would have to do 2 pi over 12, so whatever. But at the end of the day, the angular velocity isn't changing. So any interval we picked would work just fine. Okay, so now we have angular velocity. We know how to calculate that. Let's make the step up to angular momentum. Right? Not all things that rotate behave at the same angular velocity act the same way. Why? Well, they have different rotational inertia. So angular momentum is capital L. That's our stand-in for P. And I is our rotational inertia, which is basically our rotational mass. I'll talk about how to calculate that next. But for now, just think of it as, like mass. Where, like I compared like the carousel to this chair, they could both rotate at the same angular velocity but have very different angular momenta. So that's, we can use the same kind of thinking to think about large momentum versus small momentum, where how fast is only part of the story. We need to know something else about the object. Same direction as the angular velocity as well, right? Because I is a scalar. This rotational inertia, rotational mass is a scalar. So whatever direction the angular velocity is the same direction as the angular momentum. All I need to do to add to this picture, I guess, is just say that this hoop has rotational inertia I, and so now my angular velocity here's my angular velocity, my angular momentum is in the same direction, just multiplied by I. Not much more we can say about it at this point. So let's figure out how to calculate rotational inertia, or not figure out, but let me tell you how to calculate rotational inertia. We do it by summing over the mass elements of an object. And what I mean by that is, objects you can think of every object is made up of atoms, right? So at the base level, we could think of, you add up the mr squared, which I'll talk about what those are in a sec, but each element, you add this expression. So the sum is just saying mr squared of this piece plus mr squared of that piece plus mr squared of this piece. The m meaning the mass of that one mass element, and r is the distance from the axis of rotation. So from wherever it's rotating around, how far away it is from there. So if we take a look at this chair, the axis of rotation is around the center, and if I wanted to find the rotational inertia of it, I'd have to add up the mr squared, so the mass of like this piece, plus its times the distance from the center squared, plus the mass of this piece, times the distance of the center squared, plus the mass of this piece, so on. So this is a really complex object to find that for. But the ones you'll have to calculate, it's just like a few pieces that you have to add up. We'll try that in a sec. But this acts like a rotational mass. And because of this r squared, it depends not just on the object's mass, but on its orientation or its geometry. Right? You have two objects with the exact same mass, but if one of them has that mass farther away from the axis of rotation, it's going to have a higher rotational inertia. So the further away the mass is from the axis of rotation, the harder it will be to spin, or the harder it will be to stop spinning. And with that, it depends on the axis of rotation that you pick. This chair doesn't have one value for rotational inertia. It has a value for each different axis of rotation. The most natural one is about this central axis that it spins easily, but I could also define the axis of rotation as the center, like going this way, in which case it would have a very much higher axis of rotation, as we can see by how hard it is to turn. Yeah.
So when you say like pieces of an object, are you talking about pieces that are moving essentially? Like
they don't need, so you get, like this chair still has a rotational inertia when it's still, just like an object still has mass when it's still, but it comes into play in the angular momentum when we multiply it by the angular velocity.
So would you, like if you're trying to calculate the pieces of that chair, would you also look at like where the wheels are?
Yeah, well, I mean, well, the wheels aren't spinning, so the chair is a complex example. I'm going to calculate some simple ones in a sec. Yeah.
You said a higher value, the harder it is for it to stop moving.
Yeah, just like with mass, the larger the mass of something, the harder it is to either start it moving or stop it from moving. It's like inertia. The same thing.
Or changing.
Yeah, exactly. Yeah, the higher the rotational inertia, the higher the angular momentum. So let's just do some examples. It's probably the easiest way to see this. So we have a very simple, the most simple system you can have here, a single mass rotating around this center point, just attached by some massless string of length r. We've seen this in DL, right? Just a ball going around in an orbit. And so there's only one mass element to sum over. And so the rotational inertia of this is just mr squared. We have one element of mass, a distance r from the center, and so the rotational inertia is mr squared. What if we doubled the mass? We have one object of mass m, of mass 2m now, distance r away. We plug that in, we get 2mr squared, right? The m is 2m, and it's still a distance r away. So we doubled the mass, and we doubled the rotational inertia. What if instead of doubling the mass, we doubled the distance? So say it's 2r away. Now when I plug in, I get m times 2r squared, or 4mr squared. So we double the mass, double the rotational inertia. But if we double the distance of the mass from the center of rotation, we quadrupled the rotational inertia. So maybe we could have seen that just because it's m times r squared, but the distance that the mass is from this axis of rotation comes into play more than the mass. So you can make a very big difference to the object's rotational inertia, or how hard it is to rotate it, from reconfiguring it, from just making the mass further away. Yeah?
So our mass, or the mass element, you get a component of...
Yeah, so well, why don't we try one with multiple mass elements? So now we have like kind of a dumbbell rotating about the center. Right? We have one mass, it's rotating about this center point. We have one mass on this side, a distance r over 2 away, and one mass on this side, a distance r over 2 away. And so now we actually do have a sum. And we just have to sum up this piece, m, and it's a distance r squared away, plus the other piece. So the two terms are identical, but you just have to add up that expression, mr squared, for each element. So that's what I was trying to say, where the scenarios that you'll have to calculate from scratch will be not much more difficult than this. Just like, here's one piece, how far is it? Here's one other piece, how far is it? And just add up their mr squareds. We can do much more complex examples, but we'll just usually just give you that number instead of making you calculate it. But anyway, here we add up the two elements. So we get mr squared over 4, so that r squared, the 1 over 2 turns into 1 over 4. And we add them, and we get a total rotational inertia of this of only mr squared over 2. So this dumbbell weighs 2m, but it has half the rotational inertia of the system that just weighed 1m, one of them. Right? So this is just another example of how the mass here isn't the whole story. It's very important how that mass is arranged. And because these masses aren't very far from the center, it has a lower rotational inertia. But also, the choice of this axis is super important. Let's take the same exact object and put the axis of rotation at the center of one of these. So now we're rotating a dumbbell about one of the ends. Now we add up each piece, except now this one on the top has a distance of 0 from the axis of rotation. That mass is, we're spinning it about this point, so that mass is no distance away from the center. It's kind of an approximation because like it is a continuous larger mass distribution, but if we are approximating it as just this one mass at this point, it has no distance away, and so does not contribute to the rotational inertia. But this other piece, m, is now a full r, so r over 2 plus r over 2 away, and so we get the rotational inertia of this is mr squared. Basically what this is saying is that when you have like the ball swinging around in a circle attached on a string, that has one rotational inertia, and if I add mass to the center where that string is attached, if I just add mass there, it won't actually move, right? Because it's at the center, it's not rotating, so it doesn't contribute. Question?
So with the rotation, would that be a scalar VSS rotational mass? So we don't really care how it's rotating.
Yeah, so the r is squared, and so we don't care what direction it is, right? And the direction's not even constant. If I let this system evolve for a second, then these two are going to be at different places. But their distance from the center stays the same, right? This r is a distance and not a vector, because we only care about how far it is and not what direction, because that direction is constantly changing. And this is all, you notice we're pointing toward not caring about what point in time we look at these. So when we were thinking about the ball rotating around on a string, that was really kind of an annoying problem to do because it's just this simple thing. It's just a ball spinning around. The behavior looks constant, but the way we described it with linear momentum, it's like you have to constantly adjust for this inward force, and so the momentum's changing, constantly changing, and it's this kind of complex, constantly evolving system. But this, talking about it in terms of angular momentum and rotational inertia, that allows us to describe that system as just one constant state, where that ball has a constant angular momentum, a rotational inertia associated with it, an angular velocity, and those things are just now all in one direction using our right-hand rule and have a constant value. It doesn't matter where around the circle that ball is. So that's the value of this whole setup, is that it lends itself to describing rotation a lot easier and more consistently. Yeah.
Do we assume that like the mass is just at one dot is technically like just
Yeah, so we're assuming that this mass is like basically a point mass, that it doesn't make that extent doesn't make a big difference. So that's kind of what I was saying, where more complex objects like this chair. Before I've made like the simple approximation that like, okay, here's our center, here's our axis of rotation, and so I could break it down into like this piece and this piece, and like these pieces, but really that's like this object doesn't exist at one point, right? Like this piece of the chair has a different distance from this piece of the chair. So really, in reality, we'd have to like integrate or really just add up every little individual atom, really, to see like how far each one, like this very complex mass distribution. But yeah, you're never going to have to do that. The most complex it might get is either, again, just something like this with a few extra objects. You might have to do a little trig or something, or we just give you an object like a disk or a sphere or something like that and just tell you what the value is, right? You can calculate that with calculus, but we don't need to do that in this class. We just need to understand that objects have rotational inertia. The further away the mass is from the axis of rotation, the larger that rotational inertia, and how to calculate it in simple scenarios.
So just to summarize, like where the distance, if it's closer, you'll have a smaller inertia than if it was like longer distance?
Yeah, and so they're really saying the same thing, but not the distribution of mass matters, but also our choice of axis of rotation, right? Just because I've drawn it this way and said, in this case, it's rotating about that point, nothing's stopping me from calculating the rotational inertia about this point, or about this point, or about this point off in space. You can calculate it for any point. That doesn't mean that's what's actually happening in that problem, but there still is a well-defined value. Yeah.
So when you're talking about integrals, you mean like, is that when you're describing like everything going from like to every single point of the same object, is that called continuous mass or something?
Yeah, I mean, yeah, it's a continuous mass distribution. Okay, so now let's do an example kind of putting this all together. I'll ask, what is the and we're going to do this together, what is the angular momentum of the Earth revolving around the sun? So now it's important to note we're not talking about the Earth spinning on its own axis, right, which it also does. That we need to know something. We need to know what the rotational inertia of a sphere is, because that's what the Earth is. We don't know how to calculate that without more tricky math. But for the Earth revolving around the sun, we'll just approximate it's not a circle, but roughly a circle. We know that once a year it makes its way around the sun. So what's the angular momentum of that? And I'm giving us the distance of the Earth from the sun, the mass of the Earth, and of course we know it takes 1 year to get right back to where it was. So we can do kind of the similar math I did before. For the orbital period, 360 days, 365 days turns into roughly 3 times 10 to the 7th seconds, but it's just, 365 days, 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute, and we get this many seconds. So now we have all the key pieces that we need to calculate this. And I guess we can start with the direction real quick. The way I've drawn it here, which, doesn't really correlate to anything physical in space, but the way I've drawn it on this paper, what direction is the angular momentum of the Earth around the sun? Using your right-hand rule. Yeah, it's out of the page. So the Earth is rotating, revolving this way, and so we get out of the page. All right, so let's do the calculation. We know angular momentum. We need rotational inertia and angular velocity. So let's start with rotational inertia. We only have one piece here, the Earth. Why am I not including the sun? Yeah, there's a few reasons. One, it's not moving. Another way we can say it's the axis of rotation is right here, right? So it's the sun's distance from the axis of rotation is 0. We're also not asked about the angular momentum of the sun, the whole system. We're asked about the angular momentum of the Earth around the sun. So our system here is the Earth, and our axis of rotation is the center of the sun. And so we just have this one piece, the Earth, so we need to do its mass times its radius squared, and we get this huge number of roughly 10 to the 47th kilogram meters squared. The units in rotational, in angular momentum and rotational inertia, all this stuff, the units are kind of ugly, and they're not super enlightening, but they do work out, as we'll see later on. So kilogram meter squared, whatever, but that's our rotational inertia. Now we just need our angular velocity, which has 2 components, right? We need the change in angle over the change in time. So if we do 1 whole revolution, we know that's 2 pi, right? 360 degrees all the way around, and the amount of time it takes is 1 year, which we've just calculated in seconds. We know it's out of the board is the direction, and so we can evaluate that to equal some very tiny angular velocity, right? 10 to the negative 7th inverse seconds, which also makes sense, right? The Earth, just like the clock, if we stared at it, would take 12 hours for that hour hand to go around. The Earth takes an entire year to go around in one circle. So even though the Earth itself is moving really fast in a straight line, like this tangential velocity, the Earth is whipping through space, the arc that it carves out is so big that its angular velocity, how fast it's subtending these angles, is really tiny. And so now, just to combine it all together for our angular momentum, we multiply our rotational inertia times our angular velocity, and we get some really large angular momentum. Yeah, the numbers here aren't super valuable. Whenever you do astronomical stuff, you get huge exponents. But it was just kind of a proof of concept that we can calculate it. And simple calculations like these are super valuable in astronomy and often like the key to figuring out like what the mass of a galaxy is. And that's how we really do that, is just look at how fast things are rotating around, and then we can connect it to mass. Questions about this example? Just kind of like a cute one. All right, now we know how to calculate angular momentum. The final piece of the pie is how do we change angular momentum? And we do that with angular forces, or rotational forces, or torque is what we call it. This little tau, so curly T, it's also a vector, and just like with a net force causing a change in momentum in the direction of the net force, a torque causes a change in momentum, or a change in angular momentum in the same direction as the torque. And they are created by linear forces, so there's some relation between linear forces and torques. How do we know that? Well, how do I get this chair to rotate? Like, push on it, right? We know, like, this push that makes the chair increase in velocity, then this push that makes the chair rotate, are fundamentally like coming to say, it's me doing this with my arm. And so there's got to be some connection there. But what is it? How do we connect this torque to a force? Well, it depends not only on the magnitude and direction, that is like what is the original force, but also where the force is applied. Right? Now we can't just take all our forces and condense them down to one point, because if I push here versus pushing here, I get very different results. So let's do a little more investigation here. Which of these forces will cause this wheel to rotate about the center? So this first one, if I push here, will this cause the wheel to rotate? Yeah, it'll cause it to rotate, and we know the direction of that angular velocity will be out of the board. How about this second one? Well, this, yeah, it's really going to cause the same exact thing, right? There's like symmetry between what these two, we don't care that one's up and one's to the right. They're doing the same kind of thing. How about this force? No, if you just push on like the center of a bike wheel, nothing's going to happen. And what about this one? What if I pull on the rim at the edge of the wheel? No. So we figured something out, that the location and the direction of the force are both very important. What is the key distinction between the ones that will cause a rotation and that will not?
So F is perpendicular to the.
Yeah, so both these things are correct. That F is tangent to the rotation or perpendicular to this R here, but there's some perpendicularness between F and R here. Whereas here, well, here there is no R, right? This F is acting right at the center, so R is 0, and so that's one thing. This one does have an R. It's not acting at the center, but it's completely parallel to this R here. So let's try to talk about that quantitatively. Torque is the product of the perpendicular component of force and the position vector that goes from the center, the axis of rotation, to the point where that force is applied, which is a big mouthful, but I think like visually it makes a lot more sense. You just draw a vector going from the center, from the axis of rotation to where the force is being applied, and then look at how perpendicular the R and the F are. Right? So it is a mouthful saying vector from the axis of rotation to where the force is applied, but I think visually it's pretty clear. So now we have this connection between our linear force, F, and our torque by just multiplying it by this R. But it's not just the entire force. The F has to be perpendicular. Not all forces, like we just saw, are perpendicular to this position vector. For instance, here we have two forces with the exact same magnitude applied in the exact same location, except this one is perpendicular and this one is completely parallel to this R, right? So in this case, F is not 0. We have a non-zero force, but our F parallel, F perpendicular, how much of this force that is perpendicular to R is 0. And the way we find out how much is with trig. So this is our more general example. Not all forces act completely horizontally or completely vertically, right? Many of them, we're going to end up with some force with components of both. So here, just like we have broken down forces into like x and y, we're doing the same thing, except now we don't necessarily care about horizontal and vertical. We just care about parallel and perpendicular. Yeah?
Can we also find the R? Like, can we
Yeah, we're doing that. I'll do that on the next slide. So F perpendicular here is my opposite side of the triangle, right? If I know theta, then I'm going to get F perpendicular by doing F sine theta. And so my torque is this F perpendicular times R, or magnitude of F times magnitude of R times sine theta. Sine theta or cos theta, trig functions are always going to spit out values that are less than 1. So you can think of this as like FR is like the maximum value we could have. That's if they're already all the way perpendicular, in which case sine of 90 is going to give me 1. But as we make the angle less and less, as they become more and more parallel or less and less perpendicular, sine of theta is going to decrease, and we're going to get less and less of a torque. So as the force, we don't have to change the magnitudes, but as the, I can't quite bend my elbows like that, as the force and position vector come more and more toward parallel, the torque that's produced is going to become less and less. It's important to note that I've drawn the vectors like this so we can clearly see how how I'm decomposing F into the parallel and perpendicular piece. But this F perpendicular is not acting all the way out here, right? F is still acting at this point. So F perpendicular is acting with a distance R, not this whole thing here. I've just drawn it this way so we can see how the vectors add up. So we only care about the piece of F that's perpendicular to R. And in this case, that's really nice because it does kind of line up with the X and Y that were horizontal and horizontal and vertical that we're normally used to, right? R is horizontal, and so if we break F down into horizontal and vertical, I can just grab the vertical piece that I care about. But that's not always the case. What if R is diagonal? So now we just have like, I don't know, some plank attached by one end, and we're applying a force here to try to rotate it. Now R isn't in the parallel or the horizontal or vertical direction, right? And so I could break F down into a vector that's like this type of diagonal and this type of diagonal, so like parallel and perpendicular to R. That's fine. But since F is already so nice and vertical for us, it's already in the negative y direction, we could also find the piece of R that's perpendicular to F. So why don't we instead keep F nice the way it is and make R vertical and horizontal, in which case we just need to grab the piece that's perpendicular to F, or that comes from the cosine here. But since F is vertical, we need the horizontal component of R. On this previous slide, R is horizontal, so we need the vertical component of F, just the opposite here. But we're doing the same thing. We're finding how much of F and R are perpendicular. And so if we evaluate this now, instead of F perpendicular times R, we get F times R perpendicular. And we still get that same result of magnitude of F times magnitude of R times a trig function that reduces us to something less than 1. This is just like before. I would not recommend memorizing like cosine or sine or something like that. You just need to know what angle am I given, and am I looking for opposite or adjacent, sine or cosine. But it should always come out to F times R times some trig function. Yeah.
So you said F is, or F and R are more parallel torque is greater. So does that have to do with like if they're more perpendicular, their magnitude is greater?
No, the magnitude of them isn't changing at all. Just the more perpendicular they are, the larger the torque.
Like
So
the magnitude that the magnitude of the part that's perpendicular.
yeah, so you can think the magnitude of R perpendicular here versus or F perpendicular is growing too. Okay, so no matter how you do it, whether it's F perpendicular times R or F times R perpendicular, they're really doing the same thing, and you're going to end up with the same expression. It just depends on what trig comes more naturally to you. The way I like kind of explained it before that I like to do is just, if one of them is already horizontal or vertical, then don't mess that one up. Make the other one also horizontal and vertical. There's nothing corrected, like there's nothing special about horizontal and vertical other than, I don't know, it's just prettier. It makes me more comfortable to use that. Yeah.
We need to do problems where the force does not change direction as an object rotates. Or will the force always stay the same? Like,
good question. Yeah, I don't think you will, because then we get into just the math gets a lot harder, but the concept isn't really that much different. Good question. Okay, so this is what you're really going to be. I'm not going to do too much practice with this right now, because this is where you're going to focus in the next DL. So once you finish up collision problems, you're going to go into problems where you're really just calculating torques, and there's not even any movement. For the first bit, it's just everything here is in static equilibrium, meaning the torques and forces are all balanced, and so you're just going to get practice calculating them and making sure they come out to 0, and then just like with linear stuff, then we move on to, okay, now things are allowed to move, and then finally, now things are allowed to interact. And then you'll use angular momentum charts, and it's really the same exact progression that we did with linear momentum and forces and stuff like that. And so that's why I think this stuff really does lead quite well, and your next week's quiz shouldn't feel like awkwardly out of place, because this whole week you're going to be doing trig, and you're going to be dealing with forces, and so all that stuff is the same. The thing that you just might want to keep fresh is like momentum charts and stuff like that. Yeah?
So ideally, it doesn't matter which equation, you just still get the same.
Right, they're the exact same. And just as an example here, so that's really it. I'll wrap up real quick before I'm going to then move on to the board and do some quiz review. But angular velocity gives us a change in angle over time, and tells us how fast something is moving and in what direction. The direction is determined by the right-hand rule, which spits out something that is perpendicular to the plane of rotation. So most often we'll see something that's like rotating in the plane of the page, whether that's up on the board or on our desks. And so the direction of rotation will most often be into or out of the page. So that like kind of dot with a circle or an X with a circle. Angular momentum we get just by multiplying that angular velocity times an angular mass, which is called rotational inertia or moment of inertia. We know how to calculate that. And we get a vector that's just scaled by this rotational inertia, so it's in the same direction as our angular velocity, our angular momentum. And then finally, to get changes in angular momentum, we apply a torque over time, which we know comes from a linear force, but more particularly a linear force that is applied away from the center of the away from the axis of rotation, and not just that, but the perpendicular piece of that force. So there's a lot here, but this is just going to be the foundation really for everything we do with angular momentum and torque and stuff like that.